Hello viewers, welcome to my channel IITJ Olympiads and AP Physics with Ambarish. So today I have brought for you a classic challenge. I've been seeing this problem for a long time in my coaching career, and I find that students face a lot of difficulty in this one. Many students who get the solution also they get it in a very roundabout manner. So let me read out the challenge for you. So the problem is that a block of mass m rests on a frictionless wedge of mass capital M. The block mass is small m and the wedge mass is capital M. Okay, being connected to a spring of constant capital K as shown. This is a spring of constant capital K. The ground is frictionless. Calculate the time period of small oscillations. So this block is going to oscillate related to the wedge like this, and the wedge is going to oscillate related to ground like that. And we have to find the time period of the small oscillations. So if you want, you can try out this problem for some time, and then I've come up with a nice solution to this one. So after your solution, you can check your solution with my solution, and now I'll get into my analysis of the problem. Okay, so let's see. So before I tell you the solution, I'll just try to recap or maybe tell you some concepts that are involved. Maybe you're already aware of them. Nonetheless, for sake of completion, I'll state the concepts involved. The first concept is that kinetic energy of any system of particles is given by K is equal to half capital M VCM square plus half sigma Mi VICM square. So in this formula, capital M is the total mass of the system and VCM is the velocity of the center of mass of the system. So this is first term, and the second term is half sigma Mi VICM square. So Mi is the mass of ith particle in the system and VICM is the velocity of ith particle as seen from the system. So simply said, this formula can be roughly stated as kinetic energy is kinetic energy of center of mass plus kinetic energy as seen from center of mass. Okay, so the second term represents the Ke as seen from CM frame, and VCM here is the velocity of center of mass, and capital M is the mass of the entire system, right? Another fact you might be knowing is that kinetic energy of any two translating body system from CM frame is kinetic energy as seen from CM frame is half mu V relative square. Here mu is the reduced mass, that is if one mass is capital M, other mass is small m, then reduced mass is capital M into small m divided by capital M plus small m, and VREL is the velocity of one body relative to the other. So this is obviously magnitude of the velocity as seen from the other body, magnitude of one body as seen from the other body, that is the kinetic energy as seen from the CM frame. Okay, so now just these two facts and we are now ready to do it in a very smart manner. So let's see. Let's say let x be the displacement of small m relative to the wedge as measured from the natural length configuration. Of course in the equilibrium there will be some stretching, but there will be some natural configuration also. So let's say x is the displacement or maybe the coordinate of this block relative to the wedge as seen from the natural length configuration of the spring, and let us say the v be the velocity of this block relative to the wedge. Okay, so then what is the velocity of center of mass? See, now you know that center of mass of the entire wedge plus block system is not going to have any velocity in the horizontal direction. Why? Because there is no external force. So center of mass can only have vertical velocity, right? And moreover, the wedge cannot have any vertical velocity because it's moving parallel to the ground. So whatever is the component of velocity of this block in the vertical direction, that will contribute to the vertical velocity of center of mass, right? And suppose its velocity is v relative to the wedge in this direction, then relative to ground, this velocity component will be what? That will be v sine theta, right? And therefore, what is the vertical component of velocity of center of mass? By the way, since it has got the wedge has got no vertical velocity, so whatever is the vertical component relative to the wedge, same is also the vertical component relative to the ground. So we can say the velocity of this with respect to ground in the vertical direction is v sine theta. So that means what? That means the velocity of center of mass of this system in the vertical direction then becomes VCM is equal to small m v sine theta upon capital M plus small m. I hope this is clear. The velocity of center of mass in the vertical direction, right? And horizontal velocity is of course 0. Okay, so this is the first term for that I'll be requiring for kinetic energy. And why is this correct? Because center of mass has only vertical velocity and wedge has no vertical velocity. Vertical component of velocity of small m related to wedge is vertical component as seen from ground. Okay, so now what does our energy equation become? So our energy equation you know the energy method for SHM, you just write the energy in a general configuration and then you differentiate and then you rearrange. So I'll do something like that, but something much simpler. Okay, so what's the energy equation? Half mu v square. Mu is the reduced mass and v is the relative velocity of block relative to the wedge. So half mu v square plus half total mass of the system is capital M plus small m, and velocity of center of mass is this mv sin theta upon capital M plus small m, as I just illustrated. So half mv sin theta upon capital M plus small m v square into capital M plus small m. So this becomes the kinetic energy term, right? And of course then there is half kx square and there is minus mgx sin theta. This is the spring potential energy and minus mgx sin theta, because from the natural length configuration, if you consider the zero potential energy, then it has come down by a distance x sin theta, right? So potential energy lost is mgx sin theta. So we can write this for potential energy. Okay. So now if you see, if you carefully see this equation, I can take half mu v square common from here, or you can directly see from this equation itself what's happening. So if you take half mu v square common, so there is this thing you get, and plus half kx square comes as it is, and minus mgx sin theta comes as it is. And you don't even need to differentiate. You can see that this equation is pretty much of the format of the simple vertical spring mass system, right? Or maybe horizontal spring mass system, normal spring mass system equivalent, except that instead of half mv square, I am getting instead of mass, I am getting mu into 1 plus small m by capital M sin square theta, right? Everything else is same. So comparing with normal spring mass system, this normal spring mass system equation is half mv square plus half kx square minus mgx equal to constant. So by comparison, if you see in this equation, the effective mass is changed and everything else is same, right? And anyway, this only contributes to the mean position. This doesn't contribute to the time period of the system, right? So we need not worry about this term, because when you take its derivative, it comes v and it gets cancelled off. So equivalent mass we can see for our system is simply what? You compare m with this term, right? Mu into this. So effective mass is mu into 1 plus small m by capital M into sin square theta, right? And then time period simply becomes 2 pi under root of m effective by k. So that is our answer. Okay. So I mean, for purpose of explanation, I have written so many lines, but you could easily do it within one line or maximum maybe 2 lines. Okay. And I hope you liked my method for solving this question. And if you want to verify your solution, maybe you have not written in the form of m effective. So if you written in the completely expanded form, this is the alternate expression that you will get, which is equivalent to this, okay, for the time period. So that was my analysis. I hope you liked my analysis, and if you did like my analysis, please do give my video a thumbs up, and please share my video as much as possible in various WhatsApp groups or Telegram groups or whatever academic media groups you might be part of, where other students can also benefit from my analysis. And most importantly, if you have not subscribed to my channel already, please do subscribe to my channel. My channel is not monetized. It's the love that I receive from you people in the form of likes and views and subscriptions that keeps me motivated enough to go on. Thanks a lot for watching this video, and keep coming back to my channel for more awesome stuff. See you in the next video. God bless you all.